We've been maybe slightly taking for granted, the ability to be able to collect data. Um, in the beginning, we kind of said we already had a model, so we didn't necessarily need to collect more data to train that model. And then in some of the next steps, people have been training really large models, and we talked a lot about being able to train even like models that are going to predict really nice videos, and videos are even more difficult to collect. So it'd be good, especially since the amount of interest is coming up lately, to talk a little bit more about data collection, because this data doesn't really just fall out of the sky. And there are different ways and different reasons you use different type of data collection strategies. A lot of it depends on the task, but there are many different ways to be able to do this. Okay, so let's start with this first question, and then we'll get into some of the different methods. So one of the real questions that also a lot of people are still trying to figure out, but they just assume we're nowhere near this, is how much data is actually going to be needed. So if we're gonna have some agent that can eventually, like operate and do most of the physical tasks that any average person could do, how much data is going to be required to actually achieve that? So this is where we had mentioned this concept a bit before. Agent needs to at least experience enough stuff to understand how to act. And like in this case too, and let's just focus in this class, like act as in like physically do the things that you do. I'm not saying like act as in capture what is sometimes called more social intelligence, like how to behave in a crowd and like work with people really well. This is just replicate the average kind of boring stuff you might do in the morning or whatever you do with your hands. But still, this asks this question. So how much data and or experience do you think you needed before you could do the average at home or wherever manipulation task? We'll call it in terms of like hours or years for now. Any idea how many of you could cook breakfast by the age of 4? No. Okay. 6, 8, 8, 10, 8, 10, 12. Or then how about like by 16? Could some people not cook breakfast? Okay. So I think we've got a distribution there that's kind of this shape. Uh, well, a little bit more balanced than that, but somewhere around 10 years. We had a few that were around 8, and some later people. I think I saw like one hand around 6. But this means, all right, that's 10 years of data. And there's a whole bunch of details that are going to happen here too, but let's pretend then, all right, so if we want robots to be able to perform these types of tasks, does this mean that we need to have a robot physically watching some person for their lifetime for at least 10 years? No? Why not? You looked really confident in that. Mm-hmm. Okay, but there's two concepts you introduced there. So one was like a time at which the kid starts to, I don't know, perceive the problem that, breakfast is a thing that will need to be done. But at the time before that, a kid is at least passively observing how things are going on in the world. And I doubt not learning anything about what's going on, even if it's not about breakfast. So there's kind of like this passive data concept before even thinking about, oh, shoot, my parents are eventually going to ask me to do this. So I better now like study or something like that in terms of making breakfast. But then there's the second part of what else is going on. And by that mean, like even if the agent isn't immediately practicing for breakfast, does any of the other things that it learns not help it to be able to cook breakfast in some way? I mean, like, so if I learn how to cook breakfast, hopefully that at least provides a lot of extrapolation and transfer for cooking lunch. I really hope. Maybe there's a couple of cultures where those things are really different, but none of them come to mind at the moment. Yeah. So, but we've still got, so that's maybe part of this aspect here where let's say around the age of like 8 to 10 is like, okay, that was the passive phase of figuring out and watching things happen. And then when it starts to get around to the 9, 10, 12 years of age, then maybe it's actually an active thing that's done for sure. Sounds very much like kind of like my parents were as soon as I got my license, oh, they were so happy for me to basically drive everywhere and they never wanted to drive again for the rest of their existence. Unfortunately, yeah, now I hate driving and don't do it much, even though I've driven too much. Things happen. That's part of the social behavior and acting to catch up on. Okay, so then let's kind of talk about this process. And we're going to start from basically one end of the spectrum for data collecting, and then get to one very other far end of the spectrum of data collecting. And we're going to kind of think a bit about the spectrum some more. So here, data collection for robots is actually a really weird process. And it actually started out, and it still happens actually, a lot of robotics companies, hopefully not too much in a year or two. But what people would actually do is there would be a robot arm basically bolted to this desk in some way or another, and there'd be some movement thing that the like person actually wants the robot to perform. And there'd be a couple of buttons on the top of the arm where basically the operator would program in keyframes such that you'd basically move the arm to this particular spot, push a button and say like this needs to be included in the motion. Move the arm to another spot, push another button. So this also needs to be included in the motion. So then if we wanted a robot that would like wipe the board or something like that or draw something, you'd basically like hold this giant robot arm, so it's not very intuitive to try and be able to use and understand its limits, and like rotate it around this particular motion to like make a circle and push a button every once in a while on the arm so it knows to go through all these keyframes. And that would be, as of 2 years ago, it's like the most popular way to be able to program the motion for a robot arm. Maybe 3 years ago, give or take. And that this would be the process. And this is the very like user-oriented process at the end for it to be able to do what it needs to do. So this is It's like, what are some of the challenges with this? Has anyone ever done this before, like tried to program a robot arm that way? No? Okay, you're all the lucky ones. Because then you go and rerun this thing, and there's usually some kind of like IK library in the background that's trying to connect the key points, and the arm like flips over, punches a hole through the wall, and you don't know what happened. It has nothing to do with your key points. If there happens to be a singularity between two of the points, and it can't resolve them without like sticking its elbow through a wall. So it would only ever control those things in the end. There's really no space in there to be able to adjust, certainly not to deal with like contact with other items. And what was actually a new and still pretty useful design is what people are making or companies are making are called cobots. So now some of these robots have like an electrostatic sensing skin on them. So if they do accidentally bump into a person, they stop immediately since they don't really pay attention to anything else about what's going on. But it's not a very like reactive, smooth, collaborative system. It's also extremely slow, and unless you've got like a master's in robotics and really understand inverse kinematics, there can be really odd outputs and behaviors that happen. Okay, so thankfully, this way of doing things doesn't happen too much anymore. So then what's like the next best way to collect data? So the next one is a version of this. It's still called teleoperation for robots. This is basically figuring out, all right, so now it's not, there's some like IK thing on the arm you have to drag around. It's kind of like a shadow or mimicry here. There's some sensor that might be attached directly to the person. And then when that person moves themselves, the robot basically also has to move as well. And this at least may not require quite as many buttons to push. It's basically doing the exact same process though. It's now going to record at a really high frequency how the user or operator's arm is moving such that it's going to collect some data and learn to mimic that exactly in order to be able to do things. Okay, so let's talk a little bit about this process and certainly think about it a bit more. So for one, does this seem easy to use? Like a lot of what we're going to be talking about in this particular class is But I'm going to again put on like my lazy professor or like researcher hat, want to be able to get the robot to collect and do the task I want to do with the smallest amount of work from us, because then that means it scales really well. So then what are some of the challenges in trying to be able to use this system and collect data? Hmm. Has anyone ever played virtual reality before? Games a little bit? Okay, a little bit. But I'm just saying, most people probably haven't used teleoperation on a robot before. So then what are some of the challenges in playing VR games? Just as a start for the ideas that already make this a pain. Hmm. Yes. Okay, let's refine that dexterity comment a bit more because in some ways the robot can have more dexterity, like its elbows can fold almost in entire directions. Hmm. So gaps like that. So these aren't unique to robots as well as maybe one thing I'll try to like add to this in order to people to make the connection. So like even if I don't know, if science advanced for some weird reason and we could like swap right arms for a little while, it would still be weird because you're probably a slightly different length, a slightly different weight. And those things will matter, especially if we've grown literally so used to like our own way in design that you can't just swap out things. And then that can happen. I would suspect here there's going to be a larger gap in understanding for like how this robot arm operates compared to at least some other human arm. I'm kind of familiar with its limits somewhat for myself and for others. So yeah, part of this is what's often called this version of just like basic dynamics mismatch. So like even if this arm is designed to like mimic or copy some human arm, okay, for starters, yeah, the dynamics are going to be different. If you even just to start to think about it, the length for the arm is going to be different, and that's going to be weird in some way. So then there's also, you know what, the problem of having to figure that out is not going to be the robot's problem. That is going to be the operator's problem to understand how to overcome this. So that already adds more work onto them. Okay. Any other challenges? Hmm. Um, let's pretend you're, oh yeah, go ahead. Yeah, there's probably a reason why we make robot arms because it's just like, great, it's an arm. People are familiar with how arms work. But yeah, this process was still used to try and give any sort of data or instruction to some other robot or a robot arm with a different number of links, which then becomes even more like complicated in the different dynamics. Is that what you mean? Like even there are hundreds of different robots. Designing an interface to collect data from each of them is going to be its own research project almost. And there are specific tools for many of them. Okay, great. All right. So there's also one slightly even more mundane one that you'll deal with a lot. It doesn't happen as much in VR, but there's a lot of latency. So like how this robot arm reacts to the movements is going to have some amount of delay. It's going to depend on how many students are playing like World of Warcraft or maybe something like Dota inside the room at that particular time, because they'll be consuming the Wi-Fi network that connects basically this thing to some other computer and then transfers signals back to this arm. So if you're literally though, if you are collecting data inside of some sort of like robotics lab, there you should have like some sort of rules. Okay, this time of the day, no one is allowed to stream YouTube or something like that, just in order to reduce the latency here and make it easier for the network operators. Or you'll have to have some really well-designed like mesh Wi-Fi network that might help support that. Makes life pretty tricky. Okay, do those make sense? Great, because those are what comes up a lot. And it's not even just a responsiveness in terms of Wi-Fi delay, depending on the arm as well and how cheap or good that arm is, it's going to respond either slowly or quickly. and the IK library that's trying to match that arm position. So these all put a lot of work on the actual operator. So this, you gotta be able to understand these robot dynamics pretty well. This is something where for a couple of projects, we've definitely done some robotics data collection, but we also take like 5 to 10 hours to train people to get used to even using a system like this. And after 5 to 10 hours, they're okay with it. Really more so depends on how many VR games they've played before doing this, and some other kind of like skills related to that. You can look into this. There's a bunch of papers. This is not a new thing at all. Went into looking back into the history of like when was the first like VR headset teleoperation. It was back in 2005. So this is a 20-year-old idea. Still using it. Hardware is probably a bit cheaper, but that's still a nice way in order to be able to collect data. So this is an open research area because this is still a bottleneck. So if we're talking about, remember, we need to collect 10 years of data, potentially interaction data. And where this really becomes a problem is if we're doing this teleoperation and this is any harder than it needs to be, there's really like a level of quality that comes out of this data that's needed. And if only stuff that is useful and is like super good quality ends up being kept. So that means like it might take 10 years, but in that case, those 10 years needs to be 10 years of really good data. So maybe that now means 100 years of actual data collection, and only 10% of it is going to be good enough data to keep around because the other 90% is people are going to cough while they're trying to record this. Maybe there's too much latency for that particular episode. Maybe someone was in the background of the video where the arm is, and that causes kind of weirdness with the camera. So that is also thrown out. So a lot of times, like the data that is collected and might even look okay, ends up still not quite being useful enough for it to really be useful. Okay. You can also include some depth data. So I didn't talk too much yet about like the sensors that are used here. For the moment, just think of this as there's some camera basically sitting over here, maybe just out of sight, that's looking at, uh, something like that. Usually there's like an eye. It's looking down at basically where the robot is going to be operating, and including the robot in the vision as well. And most of the time, there's going to be way more than one camera because sometimes one way to get around that needing 10 years is adding one more camera, because then you can at least collect additional data from a different angle. Okay. So, all right. So actually, in this case, I would say there's actually minimal dynamics mismatch, partly because of the design for the arm and the actual person. But there are many other types of robots out there, like you said. For example, if somehow you want to do imitation learning for a self-driving car, you don't just imitate a person walking necessarily and use that data where there can be a rather large dynamics mismatch. But here, there's been a lot of effort put into making sure that the data collected is still a good form of dynamics. But okay, so there's two different types of dynamic mismatch here. So there's the one that we've basically discussed already, where the arm is different than the actual person. But we do know that the data collected on the robot is truly correct for the dynamics of the robot right here, because we're doing teleop here. So we're transferring this mostly so that the overall behavior and motion reflected on this arm does look correct for what it's doing. So that's one like mapping, but then there's another one where the data is actually generated on this arm, and that's what's recorded. It's not kept what this person is generating, but there's no dynamics error here. So we'll get to this a little bit further, but why I'm pointing this out is like later you could just take a video of, like someone just moving their arm and try to map that through a whole bunch of machine learning directly to the other arm. But now there's definitely going to be dynamics mismatch. There's at least like the actions for the actual muscles in the arm aren't going to be known. So they'll be missing information. So there's these two problems that go on. And the reason why this one is nicer, because there's a form of no dynamics mismatch, is because there's no dynamics mismatch. We know that that data should work on this arm. There's nothing we need to do to like process it to generate actions or correct it for itself. But then there's many other data sources that are much more passive that do have this additional dynamics mismatch. Okay. The same thing where like I'm walking around right now and you don't actually have access to the actions I'm using to control my muscles. So that's at least one form of dynamics mismatch. Okay. Okay, yeah, so I wanted to get to this in a bit more detail, even though I sort of already stated it. Um, where yeah, there's going to be, I'll call it like pi human, that's going to be generating some trajectory. And in this case, the dynamics here, could be, they're known explicitly for me, but then for some other robot, you can have pi, let's call humanoid, something like that. And this person or this thing is like 5'11", and this thing is 5'10", and I'll say 500 pounds, which isn't really correct, and something like 200. So even though the motion can be the same, like the physical parts of the objects between these two end up being different. And because of that, that means like a different amount of torques need to be used at each of the joints that actually generate this. So here, even if and there are a lot of these really expensive and weird suits that people could wear where they do actually track like all of the actual joints that'll move on the person. And even if all that data was collected, it would still only be what's called kinematics information and not really dynamics information that tells you like how much the torques were actually moved on the individual joints for the robot. Okay. Does that make sense? Yeah. It's still tricky. Most of those sensors are not very accurate. So like a weight sensor, I believe in this case, would be a form of an IMU, which is like detecting the accelerations that go on at the end of the hand or something like that. So IMUs are a nice way to be able to collect some data. They drift really quickly after about a second or two. So after a second or two, they're not very accurate. Yeah, partly yes, that's half of it. So that will close part of the gap, but that doesn't actually solve the problem. Because in this part, I also noted like the other robot is more than twice as heavy. So even if it was possible to collect all the pressure information for this particular robot, because of the dynamics for this one is different, if you apply the same force to this one, it just falls down. I say falls down here because this robot is heavier, so it probably needs even more torque than the other robot in order to maintain like some sort of standing or lift to be able to get that. So it's even if you had the recorded information perfectly, it's wrong because the other robot is of a different design. So that's one, the two. So basically, there's the two types of dynamics mismatch. There's sometimes you don't even have the actual like data or sensor information, and that means that like whatever is recorded isn't correct in the dynamics. And then there's another one where it's like you can record stuff directly on that robot and everything is perfectly known. So there's kind of like these two slightly related ways in order to be able to understand this dynamics mismatch. Yeah. Other questions? Okay, because this always gets really into the somewhat weeds and details for now, like because of the consideration for these two types of things, what are the best ways to collect data? Because the nice part, well, it's much easier to collect data that has dynamics mismatch. It's tons of it, really. It's all over YouTube, that's all over the internet, but it doesn't exactly match that robot. So that means, great, there's always going to be some error in my model or the model the agent has in order to be able to replicate that sort of information or behavior. So then maybe it could be possible to like supplement that data a little bit. So maybe we can have a vast amount of like passive information for being able to observe the world because it's just like overall motions that need to be matched. And then there's that agent needs to perform that thing and then close that last bit of gap in its dynamics understanding of the world and how to perform that actual task. And that's because either like height changes or whatever, you're going to get younger. Well, you're probably going to get older over time. If you get younger, give me a call, figure that out. But through that process, Like maybe there's like less data that needs to be acquired for each like individual interaction task. This is kind of like the grounding aspect when we talk about like language models. They kind of know how do I clean the kitchen or how do I cook breakfast. It'll give some instructions, but it doesn't tell you exactly how to move every muscle in your body in timing and with respect to how the environment changes and how to perform that thing. So this is almost like what is that grounding data? How can that be collected the best? We can learn a lot from passive data. We think we're not sure if we can learn everything from passive data. So then there's kind of like these collections of data. Maybe the amalgamation of all of them gets the agent to be able to learn everything it needs. Okay, we'll get back to this whole conversation at the end once we've been through kind of a spectrum of hard to collect data to up to easiest to collect data. So this is one of the examples for being able to collect data using a virtual reality headset. The interesting part is like, okay, this was designed to reduce the like work from the operator. From before, it would be, the person had to actually like hold the robot arm and move it around. At least in this case, using some virtual reality system, well, now the person gets to see like what the robot is actually doing in the simulation and kind of like through the robot's eyes. So there's less of a cognitive load on the operator in order to understand what's going on, in order to be able to see. There's going to be like less occlusions to have to work with this arm as it actually moves. And then it can actually kind of reach in there and operate. And these days, there's some pretty good controllers for the newer VR systems. So you can definitely collect some more types of feedback in kind of a nicer and succinct ways from these systems. Um, Still have to deal with latency or dynamics. So this system is a lot with helping with this viewpoint problem. There's still going to be latency in the way the arm moves. There's also going to be kind of weird dynamics here because the arm is, it's true that at least the stuff that's replicated from the person onto the arm. So like when this thing moves, I think the like simulation of this arm is pretty physically accurate, but there's still going to be some dynamics mismatch between the human and trying to understand how that arm actually works and trying to figure out that mapping that goes back and forth. It's kind of like if you've ever tried to play a weird word game where you tried to tell someone exactly how to do stuff and they only did exactly what you said. And they probably do quite a terrible job at being able to do that. And hopefully you don't get too angry with each other. But it is an interesting way of trying to think about how to communicate, how to solve a particular task. Okay. Does that make sense? Any questions about like the VR headset way of doing things? Okay, great. Okay. One of the other challenges with using a VR headset is it's one of the things about being able to overcome the dynamics mismatch is it kind of like operating in the clouds isn't quite the right word, but basically there's no feedback. You're suddenly like controlling this 50 like $50,000 simulated arm that can like actually like push holes right through the table, but yet when you're holding like that VR controller, nothing happens. So like when you go to try and push this simulated hand through the table, your hand keeps going, but most likely the dynamics for the robot arm has some safeties even in the IK system and nothing happens. This is kind of a weird process. This is another form of dynamics mismatch, at least for the operator. So one thing that can be done instead is to use a really nice haptics interface. So haptics is basically this process where like, well, now when whatever is trying to be controlled does actually interact with something, that controller that the human holds also like pushes back and prevents that person from being able to go further. So in this case, there's this, maybe I'll look at one of, see if this link still works. Yes, good. So here you can actually look at the way the video data is collected, I think. Play. All right, remember, stop playing Dota for a second so I can still download videos for the class. Not exactly sure where this one's being slow. I'll just do stuff like this. So this will be an example. So here, this is like mimicry for these arms. I was trying to at least find a video for the haptic interface. But basically, there's these two controllers that are basically cylinders, and I think there's an extra switch for closing and opening the hand. But in this case, when this robot hand goes to reach down and actually like touches the table, the haptic interface that the person holds will also prevent that haptic device from moving any further down. So there's a much stronger connection between like the physics that's going on at the end of the robot hand and what the person is actually sensing while they're collecting this data. It's kind of like, I mean, it's winter right now. So like, how many of you have tried to use your phone while having like winter gloves on? It's not very easy without actually being able to detect the buttons and the click noises and stuff that actually happens. So this is basically an extension of that concept of being able to understand even more and feel what's going on. And now you could at least, this is kind of like, in this case, has a version of like that pressure plate option that you were asking about from before. Because now the robot can actually determine like the amount of torque that's going on. The inverse torque will be applied to the person's hand so that there's actually some amount of dynamics and pressure understanding. Well, I'm not sure why this is so terribly slow right now. Really bad timing. All right, this one is loaded entirely. And I mean, obviously there's some extra details on being able to like know even more about haptic devices, but it does at least seem that these devices do provide like an even like additional way to collect data, but also additional way to collect even really dexterous and small bits of data. Like this is not something that could be done as easily with a VR device. One, because of the VR device is this controller. It has actually a pretty terrible sensor. Well, it's really hard to control grip distance using just a little trigger inside of the VR controller. So in this case, there's at least like a easier way to be able to define how open and closed the actual hand is for the robot. Okay. Any questions about this? Has anyone used like a haptic interface before? Stuff? No? Maybe I'll see if I can get one brought into the class sometime in the next week or two. At least I know a couple of companies in Montreal that are specifically working on haptic devices, and they were curious if we wanted to use them for data collection. Maybe we can set up a little like lab where we can collect data using these different methods, and you can get an appreciation for how painful it is to use some of these and how some of them are much easier. Okay, all right, stay tuned for that. Remind me about that on Discord. Um, I guess I totally give up on these ones. Whatever. Or maybe you're all watching these videos right now on your computer. So, okay. So this allows to collect for a good amount of data. Some of this data is also included in a couple of different data sets. And it can be used for a number of different tasks. So you can even get things as complicated as being able to zip a tie cable. There's a NIST board. Okay. Because if anyone ever wanted like a real challenge, um, there are a lot of like at home or whatever types of tasks that robots are being used to be able to solve. But in the actual like robotics industry, what they have are a couple of these examples, like a NIST board. There's basically like this well understood manufacturing problem. And then if a robot can actually solve this particular task, then it's sort of like almost an award for that robotics company to show they can do those types of things. So they're kind of like pre-designed from the industry, these particular manipulation problems. Like if you can do this, great. Now your robot can like assemble an entire engine and it's got most of the complicated aspects in order to get them down. So you can look at a few of these if you want in detail, and maybe those are really good, stars or like goals that we should be aiming for in order to get robotics to do these things. And yeah, there's a couple of other tasks here that we attempted to load the videos for, but for whatever reason, the internet's being a bit of a pain today. Okay. All right. So, uh, last time I checked, most, you know, most humans have at least a couple of fingers. So, like for the stuff that we talked about before, so like even using the VR set, It's only got one trigger in order to be able to do things like collect data from open or closed. Even the haptic interface was only for if you happen to have parallel jaw grippers, which are not really fantastic at doing a couple of different tasks. So then one of the last questions, especially that companies are getting into lately, is also how to be able to collect data when you've got robots and robots with fingers. Because now there's just like this extra fidelity. Absolutely, fingers are very helpful for being able to manipulate lots of different objects, especially things that are very small and dexterous. But this means that there has to be some additional process for basically being able to track the individual fingers. This is a bit of a tricky computer vision problem. There's certainly a couple of these. Okay, fortunately, these days, there's a couple of pretty good headset systems. There's some earlier work if you really want to get into it, where you can buy basically gloves or like these wrist mounted things that also have like little tendrils that go up to the end of your fingers, and they'll control and monitor and capture the information very carefully about how you move your fingers. The problem with those is it's almost like another version of operator challenge, but it's also like a version of like Heisenberg's uncertainty principle, where if you start to add sensors onto the person's fingers, it also kind of messes with the way they collect the data because it's either going to add extra weight, it's going to slow down the fingers because now there's this rubber tubing that basically goes over top. You're just not going to interact with things the way you normally would. Also, because this sensor system is really expensive, so you're probably terrified of breaking this if you're a grad student or something like that, or anyone at all, because they don't make too many of them. But fortunately, there's been a handful of these like updated like VR headsets now that have a couple of cameras built into the front of them. And some of the newer ones, like the newer like Meta Quest or like Apple's Vision Pro, can actually track the hand pretty well with some amount of noise. And the reason why this is nice is because now there's no sensors like physically strapped to the actual hand for the person. So they can move pretty naturally, collect and interact with things pretty naturally in order to be able to do things like, I don't know, cut things or butter toast in this different process. And then where this can be nice is at some point after collecting this amount of data, you can have some robot hands. And now there can be like an additional smaller gap in terms of dynamics mismatch because now we get away from parallel jaw grippers. At least now we're more towards like humanoid hands with at least some amount of fingers and being able to track that data well. So this now becomes even more natural for people in order to be able to collect the data. The challenge is now is there may or may not be more dynamics mismatch. For example, there's really no perfect replica for a human hand. So even if the motion is captured for how the human hand moves, it may be impossible to replicate that exact motion on whatever robot hand that is created. And certainly most of the robot hands that are available, uh, they're, more different than human hands. Like the ones that aren't super expensive are kind of chunky looking and extremely breakable. But if you can, buy a few extras in order to be able to use them. Yeah. So any questions about collecting data for human hands, or I guess for robot hands in this case? No, it's something you kind of like dream about every day, so you're pretty familiar with the whole process. Mhm. Yeah. You mean for the hand in this case, right? Yeah, so it seems like for the libraries that come with these pieces of hardware, I'm a bit more familiar with the one for like the Apple Vision Pro, where it does have a bit of like a prior on the fact that this should be a human hand. In fact, to the point, uh, probably shouldn't quote me on this one, but the like if there are certain numbers of fingers that might naturally be missing, that model might actually have a hard time being able to track that hand to some point. So there's definitely priors in there and it'll map out like all of the points and basically the knuckles on the hand and figure out how those are moving and try to fit that model to both of the hands as they're moving around. This is actually a project that I've been starting a little bit with a couple of people in Quebec. They want to do vertical farming indoors. And the idea is basically, put the VR system on top of people that are currently operating. They're actually picking strawberries, and then basically be able to collect that data and then train some of the robotics models, probably with better human hands at the end of the robot arms to basically replicate this motion. And the idea is of being able to figure out and like look at things, whatever the farming people do, to be able to monitor the general growth and picking process. So yeah, it does work quite a bit. I will say one of the weird things is at least there are far more robotic right hands than there are left hands, which is a kind of weird problem, but it's just the way current manufacturing happens to work. They're not exactly the same, so you got to choose to design one or the other. And I guess we'd start making a right hand first and then make a left hand eventually. So we'll get to that process. Great. Any other questions? All right. Um, yeah. Okay, so now this is like one more step from the cyber a little bit more to the physical. So it's possible to maybe be able to match the hand and be able to map that to a robot. But it's also because of part of the dynamic mismatch problem, whatever data that's recorded from the person may not replicate perfectly onto the actual robot because of a dynamics mismatch. All right, one kind of interesting way to overcome this. Okay, why not basically put the robot hand in the human's hand? So then at least we know that the things, which is the data that is collected, is stuff that can be performed by that hand. Like the friction coefficients will be the same, the gripping style is still going to be the same. The overall motion will work on the robot now. Should anyway, now that the actual gripping for the end of the hand is the same. You see what I mean, sort of in this picture? So for this particular paper, there's basically you can get a 3D printed copy of the manipulator that will be mounted on the robot. And then you can also hold that in the hand, and then it'll record basically the like open closing action for the hand. I believe there's also an IMU and a camera on this. So it's basically all the end effector pose and gripping information that is used to actually determine where the robot arm will go. And this is possibly a bit nicer because here there's no, at least versions of dynamics mismatch, especially contacts, because contacts are some of the worst places to have dynamics mismatch. So even if you, I don't know, seemingly match the human hand poses really well, because the like torque isn't matched very well when the robot goes to pick up objects, it just falls right through the fingers because it doesn't understand how much that needs to be gripped. Here, there will be like sensors for understanding like how much to actually squeeze the object in the actual scene. And then this can be used to collect a lot of different data. This is also a kind of common view, which is basically kind of like called the eye and hand view for a robot arm, such that it can collect this data and then be able to even use this view information to understand how open or closed the robot hand is. And then from this process, you can basically map now the hand and like reverse engineer those motions and understand the dynamics of what should be used as well. Okay. Handheld claw. Let's at least try to look at the video for this one. Maybe this will work a little bit better. I've got a theory for why everything is so slow, but I'll check that in a minute. All right. Oh well. All right. Any questions about this sort of like adjusted way of doing things? Okay. Yes. Well, before we would need one VR headset per person. And now we've got one or two devices per person. Depends on how many 3D printers you have access to, how you might be able to scale this up. I think the actual bottleneck is going to be the number of cameras that are mounted on these more than the 3D printed part. That looks like some sort of GoPro mounted on here. I mean, for this particular paper, yeah, there's like a design provided for the particular gripper. So in that case, you might need this specific one, but I would say if it's possible to 3D print other versions and kind of follow, like the overall style of what's being mentioned in this work, which is just if you can make what is now called not a digital copy, but I suppose now like a physical copy of what's actually going on in the robot. That means like you could use this process. So even if there are other types of robot grippers, it might be possible to like 3D print something that even attaches on to a current type of robot gripper that is in use quite a bit, and then be able to collect this information and this pressure information, and then have more dynamics matched data for the actual robot. Mhm. Yes.
It's really awesome here that the person is doing or performing the task while using their eyes, you like kind of reverse. It's easy to perform a task where it's not actually on from the point of view, like maybe like long-term plan or the group is kind of like tunnel vision. They don't have a good view of the whole team. Like
Mhm. Yeah, that's always at least one of the trickier aspects of dealing with these. Maybe, and it seems like for some of these tasks, because there's two hands, one is kind of used like a top-down camera while doing the other part. But again, this is like load and effort put on the actual operator to understand what's actually going on. Yeah, but this is maybe a different part where maybe on top of this, someone should be wearing, I don't know, maybe Meta's new VR, AR glasses that don't look entirely stupid, but whatever. Just so you can record like the visual information. And even that's not perfect because still people kind of look off to the side when they're doing things, so it might be missing some info. So that's a whole nother problem that I currently suspect, yeah, the community doesn't have great solutions for that. Even for like all of the data collection that we've talked about so far, there can be essentially occlusions or partial information in the data that was collected that the person was either using somehow during this process. The only real way to check whether or not all the data that was necessarily there in order to perform the task is to train a model and get it to work. If it doesn't work, well, it could be one of 50 things, but one of them could definitely be there wasn't enough information to determine what should actually be done in that task, giving the camera views. So I don't know. Duct tape a bunch of cameras to yourself and maybe put some more cameras on the ceiling. At least that seems to be what people are doing more so these days because cameras are still kind of cheap. So just try to record more data. But even then, that's still a challenge. And that's actually part of one of, okay, the last question for the homework assignment, which I removed because I thought it was too much work. But basically, how much does image resolution matter? So like even if you're recording data, some of the cameras that have recorded data are lower resolution than human eyes. So that means like the stuff might be in view, but there's not enough pixel information to capture what someone was focusing on during that task. And that's certainly been one of the key ingredients in being able to get some robotics methods to work better in the last 2 years is literally now we have enough compute to handle what are still actually small sized images, like 256 by 256. 2 years ago, everything was 64 by 64 at best, and everything in the screen had to take up at least 10% of the space for the machine learning model to ever pick up on it. So that's still going to be practical systems challenge for the next little while. Yes.
do you also like for actions?
Mm, so I don't remember the details exactly. I on
I read this paper.
okay, go ahead.
It's like they use slam or the first they map out the whole environment around, and then they use like visual slam forms time, and then get the code in the map.
Mhm.
They define the role frame, so they map the whole environment. It's not as and you go somewhere. Yeah, but for map out
Yeah. I guess it gets a bit of the info from the GoPros with an IMU.
Yeah.
So you're basically doing SLAM based on the sensors for these cameras after mapping out the environment. Mhm. It seems like it's relative to the bottom left corner of the room after like mapping out the entire room or some center location in the room, which isn't can actually pose some weird challenges in terms of like transferring and reusing this data for other robots or other size rooms. But yeah, I think there's still a few more steps in order to make this more usable for sure. Yes. Mm. Well, at the moment, this would be just data, and then depending on how the data is massaged a little bit, can be used for different types of learning. So this is probably going to be used for behavior cloning. Um, and maybe one example of this, which is done right now, and you'll get to see some of this for homework too, is essentially the output for the behavior clone policy is this, where it's just going to be the rotation and location of the hand and whether or not this gripper is closed or open. So then basically the input is just take in these two images, or really just one image of where the current robot is. Where should the next step be for where the hand should go? And that's basically all that gets learned in this process is like current state or observation, output, what is the change in action that would happen right now to get to the next spot. So basically in this situation, next action should always be this next part. In this case, because some dishwashing is going on. So the next action that follows is always this. Although there can be some weird problems there when you actually record a bunch of data for the same task and things are slightly different, because then there's not a one-to-one mapping from inputs to outputs. But that's a whole class basically that we'll talk about later on how to deal with kind of multimodal output distributions depending on how you collect data properly. But that's like one way to start using this. And then maybe when you train some policy like this, you can start doing RL from after training some policy on this data in order to maybe correct some of those, I don't know, mistakes or also places where data has been duplicated. Okay, any other questions? All right, let's take a little break. What time is it? Yeah, 2:30. Let's take a break till 2:40. And then I Oh, sure. Yeah. Yeah, go ahead. What time is that at 4? Sure.
Hi, good morning. I'm Shing. I sent the message for you to audit this class,
Mhm.
but I want to discuss what that I can separate my homework project if I'm right.
Uh, uh, I mean, there's no auto grader for the class. So we just kind of visually look at stuff and see whether or not, some amount of learning has been achieved.
Okay.
So I don't think you'll need to be on Gradescope for that. So you can just check. You do have access to the Montreal Robot Learning GitHub where the homeworks are.
Yeah, yeah,
Okay. That should be good for now, because otherwise there isn't really anything. And for people that are auditing, I don't grade their assignments. That's extra work. Yeah.
I will try and I will send my homework to EA. We will
I mean, for homework assignment one, there was a few test cases inside of the code that you could use, do some evaluation, but there's no real testing for homework too. I'm going to send an example of what a good learning curve looks like, and then everyone should attempt to achieve that. And that's what we'll be grading as. Yeah.
Thank you. How about message?
Okay. All right, sure. Hey, sure. Mhm. Basically, we have these ones is one way to start using them. So if you look at the Aloha paper, we have a lot of these robot arms that people can use. No, this is a Trosson Viper, it's the Viper X250 or 300. These should be 6, from what I know. There's like the base rotations and then the different joints for the elbow, wrist, and then the gripper. I think there's still 3 joints here at the end of the arm. Uh, yeah, that's why we have these arms. These are one of the much easier to program arms, so people can kind of get started with them already. And we've already got some software for them and a API for using them. Okay. Yeah, give that a try. Do be a bit cautious about that. And by that, I mean, so like for the robot arm that you have, if there isn't a software library for it that'll make it easy to use machine learning, then we should chat because that might be, I'll put it this way. I can't give you a grade, like a good one, for just like creating an AI library to control your robot or like just a library for controlling your arm. I can give you, I'm going to grade people on like what machine learning they did over like data and with the hardware they use. Potentially, I mean, it depends on how much work it is. Hopefully for this arm you've got, there is a library already for controlling the arm. And then it should be far less work in order to be able to use it on that robot arm. Yeah. Mhm. 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 Okay. Sorry. Okay, but you don't want to make the project too large. You know, pick something where you can get into like the machine learning aspect pretty quickly, and that you can uh, find something that'll be interesting to be able to learn and perform. So yeah. Hmm. Yeah, that could be good. Yeah, definitely have something that's like a collection of milestones. So it's sort of like the bare minimum that I know like I can get to this one, and then getting there will also show that machine learning has been used, somewhat successfully, then that's great. And then everything after that can be just like a bonus for like if things progress past this point, then things can become more and more, I don't know, involved if we get that far. But I want to be cautious on setting projects that are like huge in scope because then like I want people to learn stuff from their projects as well. Yeah. Mhm. Mhm. Okay. Yeah. Yeah, that'd be good. Sure. All right. Sounds good. Yeah. Sure. Yep. No problem. I think the robot, the hardware that's already available is also on the web page for the course. Okay. All right. Mhm. Ah, all right, everybody. Let's get started back up again. So we were getting to some of the details, and I guess I just wanted to review for 1 second, like those two different types of dynamic mismatch. Just remember that there's one that basically exists inside of the human's head when trying to like teleoperate some interface, but at least there's no dynamics mismatch on the data that's recorded for the robot. And then there's the other part where basically there's just some data recorded of the human, and then that's trying to be like replicated onto some sort of robotic system, and there can be dynamics mismatch. The same way there's dynamics mismatch between any two robots that aren't exactly the same. So that's where those two different types can basically kind of cause some of the mismatches that occur between these two problems. Okay. All right. So now we've basically talked a lot about hands. So now we can get to some of the more other ways in order to be able to collect data. So this isn't just for a handhold claw. So another way to do this process is basically entire like body motion capture tracking. So in this particular work, the idea is, okay, it's not the like from vision manipulation task that's trying to be solved here. It's the kind of humanoid behavioral motion matching task. So here that like maybe the person is trying to do some sort of dance or some sort of walk or run and then being able to replicate that particular behavior. And then here, this was done like online, as in the motion position information from the person was tracked in real time. And then some version of something like IK or inverse dynamics is used to have the robot basically replicate that particular motion. So this isn't like using as much machine learning, but this is certainly a way to basically have like some sort of mirrored robotic system. And now this is motion capture because it's tracking the entire body, not so much the hands here because that isn't is not as much of an interest. But we're kind of slowly getting further away from tracking, very detailed things about what a person is doing to now like more and more just like general behaviors at a further view from the people that are actually doing the motion in this particular case. So this works surprisingly well. Like this was already done. How long ago was this? Not too long, 2008. So not quite 20 years, at least 15 years in order to already be able to do this motion. So this ask a little bit of a question about what's different from things back in 2008 compared to now. We can already collect data for humanoid motion. I suppose the differences these days is being able to like make an AI system that's going to replicate this behavior, like understand when these motions should happen when it goes to move in the actual world. And we're slightly better at making hardware these days. And actually, I wouldn't say we're much better at making hardware, depending on who you ask. Okay. So then there's beyond this, because this only works inside of a mocap system. And if anyone has ever used a mocap system from before, it's only going to work inside this very special room when the human being is wearing these little reflective markers on their body, which you probably can't see too well. Okay, then. Let's go back to that. These little circular things that are used to basically capture how the person is moving. And those need to be attached. And if those move at all, you basically need to go back and recalibrate the motion capture system because the motion capture system will now think that the person's arm is like grown and then the dynamics and kinematics mismatch will start to grow as well. So this makes for still a pretty brittle system that requires a lot of very careful planning, as in it probably took like 2 weeks in order to just to get to this particular experiment after figuring out how to calibrate the mocap system, after getting the robot to actually copy this pretty well, and then finally getting it to kind of match in somewhat real time. So it means this is going to be way too difficult in terms of collecting a lot of motion capture data at scale in order to be able to train robots. So we can hope for maybe something that's easier to collect, but now is going to have, less pure information, kind of related to some of the questions that have already been asked. But analysis, like how much can data from the wild be used to be able to train the robot system? So in this case, this is first person view stuff, so not even third person view yet. So here, this isn't using motion capture, but now it's kind of like this extra process of like looking through the person's eyes while they're actually performing individual tasks. So it's the data that we all use in here when we're performing whatever it is that we're performing. And then from this, basically trying to either learn some type of representation or possibly be able to train some robotic system to be able to replicate the behaviors in these data sets. So this is part of either the ego for the Facebook kitchens data set, where there's a bunch of basically people that put, I don't think there might have been GoPro cameras basically in front of them and then just went through their normal kitchen cooking, cleaning operations in life. So that there would be some basically first person interaction data in order to be able to train a model. And then there's this slightly different version, this Ego 4D, darn it, data set. If I do that, which is a little bit different than the kitchens one. This is a little bit more like extra third person data. It's all from additional view to see what's going on. So the nice part, as I was saying, the data here is really cheap to get. The problem here is that there's essentially a really large dynamics mismatch that can exist amongst other things in the actual data. It's unfortunate, but supposedly, this is how people learn. So there should be enough data here through some mechanism or another in order to be able to train agents that can perform a lot of the skills that humans do. But it's also just a very low quality data set. And that can sort of have a lot of its own problems. Okay, does that make sense? Any questions about like the type of data that exists here? Everyone kind of has the idea of what might be in it. Go ahead.
Just using this data for pre-training visual like base models is better because it's more of like I guess you're assuming the robot the points of view you'll get from here are more closer to a robot versus like training the kind like cats and dogs.
It would be closer as it looks like for a humanoid robot. So like not for a self-driving car. I don't see too many car, at least videos from this particular clip. But the question is still how to actually use this. I mean, like what particular training pipeline would you put this inside of in order for it to actually help learning? This can't be used for behavior cloning. There's no action information in any of this. So that means we can't use what was used on the, I don't know, the two slides ago, where there's the like physical option to actually have that hand. So you can just use behavior cloning. This is, suppose maybe this can be used for some type of representation learning to begin with, but even that's questionable. Um, Part of that is also like a separate question. So if we were to rewind a bit to like 4 lectures ago and we were talking about video generation models, what was the distribution of videos used for video generation models? Kind of stuff from the internet, which has, kind of an odd style. I mean, the stuff that ends up getting generated from these are kind of like scenes from nature, which is sure looks beautiful, I suppose, even though still there are a lot of things get really kind of gumbled up. But I think part of what I'm trying to get at with that is a lot of those scenes from nature, they're still very fully observed, the stuff that was generated. Not a lot is going to come in and out of the view. When for all of these, like the camera view is changing a lot. Shoot, I did not put the link for this one, but if you look at like the Facebook's kitchens, I think like for every couple of seconds, the camera view changes entirely. People change what they're looking at a lot when they're doing things. They must have a very good short-term memory. Basically, it's kind of overcoming all of this change in location, the way they look at things. But maybe what I'm also trying to say is, well, maybe we should be training those video generation models over this stuff. This is like, okay, now the agent must learn memory really well, handle like changes in view really well, generate stuff from first persons. And if it starts to do that really well, it'll actually be tracking like the objects that are the useful objects in the scene much better than just down to like maybe detailed pixels about how the wind and water is moving, which isn't, as important. And it's okay to make some errors about how the water is moving because it's not going to make like the robot drop the object it's holding. So there's possibly some more useful information that could be extracted here. And if someone trained an awesome video generation model from this data, at least I'd be more impressed. But obviously, I have a pretty strong robotics bias for, okay, now it actually understands the distribution of things going in and out of the scene, depending on recent history, much better. So those are at least some of the places I suspect this will be potentially useful. It is kind of related to where I've seen people use these data sets. I think the Facebook Kitchens data set was also used for the, was it the R3M, like robotics manipulation representation paper from 2 years ago. That means that maybe this was kind of useful. So I suspect that, yeah, like pre-trained models on these should have good perception models for robotics and hopefully model the dynamics in the scene a bit better. I don't know how much the Ego 4D dataset has been used for robotics yet. I know some of it, I think, has been used for some of the segment anything models lately, or at least a test case. So I suppose if you take a segmentation model and then just use that as a pre-trained model for perception, yeah, maybe that'll be helpful in robotics tasks. Okay, other questions? All right. So all right, so this is a bit of a picture here. And this one's a little bit more hand wavy because there wasn't really a picture that represents all of YouTube or something like that. But now there's also a lot of like third person view data. So this isn't really like you of yourself watching, the robot do its own thing, but there's a lot of data that's collected now on YouTube that's available, much like the rest of the internet. And there's also now think about like the process that could be used for this data and what can be learned from this data. So it's not going to also have much like action data in this, so it's not going to be very easy to be able to use for behavior cloning. Although there might be some ways to be able to like now use some data either from both of these, like this data set or even third person to do now some sort of inverse dynamics where maybe some actions could be labeled for some of the videos in this data and then transferred to other particular videos. That'll be a bit trickier here because of how unstructured this data is. Yes, especially stuff like this. I'm not exactly sure. Totally what'll be learned there. But one of the nice parts is because even for these particular videos, it was kind of that weird process again, where the person is wearing like a helmet and a camera. So the way that person might do things is not going to be as natural. But the data that exists in this like third person view, that's just like collections of data. You can also think of like every single video that's collected for some sort of sports match ever would also be a good like source of good quality data for good motion. But there's going to be this large dynamics mismatch. So maybe one way to overcome this is to figure out how to perform some really good form of inverse dynamics modeling, such that given the agent or whatever that's in the actual video, train a different model to predict the actions that that thing is actually doing inside of the video is one option. But there's basically, if the problem is that we don't have enough data, and if like we need 10 years of data, possibly something like YouTube is a good source for tons and tons of data that can overcome that. This should be like all the passive data you need. Maybe this plus everyone's, what do you want to call it, like at home family time videos and not just all the weird stuff that's on YouTube. Because YouTube is still full of weird stuff. I don't know, I'm not on it too often, but it's not always just people doing like amazing backflips all the time. Is that what everyone actually goes to view YouTube for? You're probably not studying the motion of the people inside of every one of the videos that you do. It's probably a lot of weird other stuff, maybe not so weird. So like even if this is a route for the way forward, someone or something is going to have to come in and like, sift through all this data to get the stuff that's useful for robotics motion and isn't just, I don't know, other extraneous information. That's going to not be as helpful. So that'll be kind of like process one. This will probably be somewhat like the process of being able to train an LM. The first step, which basically everyone ignores, is create the internet. The second step, which everyone also ignores, is figure out how to select the top 1% of all the stuff on the internet. Luckily, some of that stuff was already done for LLMs. And then step three is like, okay, like maybe train something to replicate that good distribution of data that you've managed to capture. But we still need to figure out those first two steps for robotics. Still need the data, and we still need good quality data. So maybe that can be processed from this. Who knows? It's not quite as obvious on what to select on what are good videos. Maybe taking actually stuff from a lot of sports would be a good one. Or you probably wouldn't be able to get the licensing rights, but maybe taking a lot of cooking shows from TV or something like that would be another good option. Who knows? Okay. Any questions about uh, the benefits, but also like the hurdles and being able to use third-person data? Pretty clear for now. Basically, it'd just be really nice if this can be made to work. The the challenge is, and I guess we'll get to in a bit, like I said, there's not a lot of good information. So somehow this needs to either be sifted through or extracted in the right way. Okay, so everything of what we talked about so far is like collecting real data in the real world, but it's also possible to simulate a lot of this data. There's going to be some boundaries in what can be simulated, but for some cases, like for example, it can be really hard to collect certain situations. So that maybe the company has spent already a bunch of money collecting a bunch of data, but they forgot to collect some for a specific robot or at a specific time of the day or for a specific task. Do we really want to go back and like figure out how to reconfigure that robot and maybe like buy another kitchen to add some variety? Or can we just simulate that data diversity? So this is one of the many advantages of basically being able to simulate this data generation process. So there's this paper from a couple of colleagues where they're using the Orbit simulator, which is based on Isaac Sim. And because it's kind of like well crafted and by NVIDIA, there's definitely some pretty good uh, like details and appearance that actually exists. So the things that are simulated inside this environment can look somewhat realistic. There's maybe a few details that are always missing. Basically, all the simulations inside of the simulator look too clean. It's too perfect. Like this wall that is like perfectly met and the background is never going to exist in the real world. Hopefully the model learns to ignore these types of things. But that doesn't mean that the data is like not useful in some way. So here, some of these scenes could be used to generate some additional data that you can still train your model from. And if you're doing maybe some projects in the class, this might also be a good way to like do some of your simulation, some of your proof of concepting for your algorithm. If it doesn't work here, it's unlikely to work in the world, depending on the types of problems you're interested in. If it's mostly about appearance, always be a little bit careful when taking data from a simulator if it's about contacts. So this particular one, it's like a hockey stick and a puck and a couple of objects interacting together. Simulators are notoriously terrible at modeling that part of physics, things like friction and contacts. And data transferred or policies trained in a simulator usually struggle when it comes to contacts, depending on how they're modeled. Okay. The nice part is a lot of data from this real quick. Just hopefully it's useful. Okay, does that make sense? Has anyone ever generated data from a simulator before? A couple times? Yeah. So it's definitely can help augment your data. Maybe one good recipe here is actually to mix this with some real data. And then at least you've got some grounded data. If anything you take away from this lecture today is like you almost always need some true grounded data, especially something that's near the task you want to solve. This other stuff might help to add more robustness, but if the agent is only going to learn how to understand to do the task if there is true grounded data of what the task actually is. This other stuff would be like, well, maybe generating a whole bunch of random scenes here will help the robot learn it can ignore the background because you can basically generate anything there now. That's unrelated to the task entirely. Okay, great. Right. So said lots of good things about the simulator. All right, for some people that have tried to collect data in a simulator before, what are some of the challenges of collecting data in a simulator? Just some. I know there's definitely a few. True. Yeah, like even I don't know, the lighting and the way the lighting works looks pretty good inside of these environments, but it's not exactly what'll be in the real world. It tends to be more random sources of light, for sure. What are some of the other options? Mhm. Yeah, they're kind of They're perfect. They're like over ideal. There's no friction in the robot, at least for most of the simulators I know. I've seen friction once or twice in some pretty complicated simulators that end up being pretty slow. Because yeah, to model friction is making your simulation slow. And some groups are only interested in having the fastest simulator in the world, at the expense of other things. So there's that. What about some other challenges? There's one kind of tricky one here that at least we haven't gotten to yet. How many people have created a simulator before? How long did it take to make the simulator, give or take? I guess nobody since that. And I won't take this as an example. It takes so long, you all haven't lived long enough to make one. But I don't think that is true. But it's really hard to make these. So like if you wanted to add some more items.
Even like
Yeah. So I don't even, I mean, there's so many ways to go with this. But yeah, even just trying to set up like this simulator in the beginning, like this is a really nice looking simulator. It's also enormous in terms of like compute that it needs, space it takes up on your computer, requirements to actually be able to install in order to be able to get these things. It's almost like you're better off just collecting data in the real world that you know is grounded and captures the proper distribution. But yeah, be careful about that assumption entirely. Although I definitely have like myself and a couple of colleagues who've almost entirely given up on simulators. Like the time spent on the simulator is actually a waste of time, especially for a certain number of tasks and certain kinds of tasks. If your tasks have a lot of contacts, I suggest you don't bother using any simulator at all. It will not work. So just go and collect some data and have some fun learning to become good friends with your robot, and that'll give you much more grounded and useful information. But yeah, but also in general, just like if you wanted to add like one more robot arm into this simulator, that could take weeks. If anyone's ever tried to program like a URDF file from before and get it to be obscenely perfectly accurate such that it lines up really well with where the fingertips are and everything, yeah, you'll spend weeks working on that. So there's maybe someone should also be working on like AIs to help program these better. And I know some people are. But otherwise, just be cautious of these things where like a simulator might sound like less work than a robot, but it actually may not be less work than a robot when you really think about it. Okay. So that's the short list of challenges. And that's where, yeah, I kind of wanted to have this chat. What tasks do we actually care about? The real world is not a grid. So if we're going to make choices between using a simulator or where we're going to go and collect data, what tasks do we actually care about in this room? So like maybe I should pick on every person individually to see what robotics task you're most interested in. But yeah, any ideas? Like what are we all hoping in order to be able to get a robot to do by, I don't know, next year? Okay, by the end of the class. Maybe that'll be more optimistic. Nothing? Hmm. That's a good one. Okay, check it in. What else? Breakfast. Okay, we've at least got one person who uh, likes breakfast. All right. There's a lot embedded into breakfast, but no. What else? Okay. I'm gonna call that depth analysis, sort of something like that. I think it also, in your case, kind of includes perceiving, but also estimating how long it takes to get there. Other ideas? Okay. Okay, great. This is already a good start. And let's put all of these, because the real question is, okay, what data are we going to need in order to be able to get an agent or some agents in order to be able to perform all these tasks, or even some subgroups of them? Is this something that would be easy to program in something like this in order to be able to collect data? For self-driving cars, people have been working on making self-driving car simulators for decades, and there's still, no, there's definitely still some challenges. There's a lot of mundane details. In fact, NVIDIA keeps asking me, it's like, all right, how can we make more realistic humans inside of the car driving simulator? So that at least when we deploy the simulator in the real world, it'll react to natural looking people and the way they move, and it won't start running over people because they look and walk differently in the simulator than they do in the real world. Seems like a real concern. Hmm. So a lot of this is just, we should really be careful thinking about these tasks because now this is going to influence like, okay, should we spend time on making a simulator? Should we spend time on collecting certain amounts of data? Where are the most useful or helpful robotics applications going to be? I mean, especially this, this, does it get even more difficult as we get down this list? It's certainly tricky. I mean, to make a breakfast simulator, this is a simulator that also has to understand like chemical dynamics of the universe. I mean, this has to do that as well, but I think this also has to do a pretty good job if you want to make like a perfect souffle or something like that. It's not really a breakfast food, but it's a start. And then figuring out how to teach kids. Yeah, good luck with that one. That one's a very interesting one. So this one is kind of beyond the, I guess, like physics understanding of the breakfast part and figuring out how to collect that data and what individual things we want to be sure that is like captured inside of this data set. Yes. Mm, true. True, but somewhat ironically, one of the best uses for a simulator is trying to collect data in areas of the state space where we wouldn't really be allowed to collect that type of data. So a lot of people are basically creating a self-driving car simulator, setting up the configuration to like start that simulator such that it's like really close to a crash. Like they're trying to artificially generate and now select crash data. And then, well, how to recover from the crashes really to avoid them because they really don't exist in the data set. They are so incredibly rare. Well, you can. I'll just say it's very costly is one way to do it. And that's really something to consider too, is are there ways in order to be able to get to the data that might be needed for some of these things without having to, I don't know, risk or incur those costs? Um, I don't know. The example I typically give here, at least for the self-driving car scenario, is I learned not to crash into things when I was really young, when I fell down a bunch of times. I do not have to get into a car and go obscenely fast and smash into things to understand that accidents and the potential for an accident is bad, despite how many speeding tickets I got when I was, a teenager. But so like there might be ways we're just thinking about, okay, what is a non-risky data set that can be collected that captures most of the understanding of the perform? Something like that. That might be true for self-driving cars. Maybe we could at least record data from people who play a lot of bumper cars or something like that. That's kind of related to this. In terms of safety, and this is where I've actually got a pretty strong, somewhat biased opinion, is actually like generalization, I believe will be maybe more key here than making algorithms that are safe algorithms. It's just because the safe algorithms usually imply a really strong model and understanding of the world, and I just rarely believe we'll have that. So there might be a way to generalize things to the point where, all right, I guess if we're on this part of the conversation, why can like people walk really well and generalize really well and work and walk and well, like outside in the snow and the ice when you've got different boots? Is it because of a particular type of data distribution they collected? And what I mean in this case is maybe one question to ask is we all grew up from being slightly smaller versions of ourselves, but through that whole time we had to learn how to remote like control our bodies and still be able to cook and breakfast even as we got older and taller. And there might be something unique and important about developing a control system while the dynamics of your world are essentially changing, getting taller and or older, and you're now robust to all of those changes and the way that is collected. So that maybe you can now transfer the like times you may have fallen over as a kid to now when you're taller, is like, okay, I still don't want to fall over and I'm now twice as tall, so it's going to hurt twice as much. So now I'm twice as cautious for those particular problems. And that there could be a lot of merit to that like particular type of transfer. This doesn't really reflect at all towards the teaching kids example, but um, that part is an important, but maybe slightly separate problem about figuring out how to work as a team, basically figuring out how to assist people cooking breakfast, something like that. Yes. Mm. So for simulation, and to be honest, I do like simulation can work very well. And for some types of tasks and problems, though, there's a different size in the sim to real gap. This seems to be pretty large for the self-driving car problem, but not because of the physics of how things go on in the self-driving car problem. I think that's been solved for a while. But it's there are other cars out on the road with a very interesting behavioral distribution of how they change and do things. And because of that, that makes a very complex sim to real gap. So that's where think about the task very carefully that you're going to end up wanting to perform with the robot. This is where sim to real has worked really well for like a stationary robot arm that has to move an object because the gap is basically just a small mismatch between the way the Newtonian mechanics is modeled inside of the simulator and how the Newtonian mechanics match up in the real world, and maybe a couple of like milligrams of weight tolerance in the design of the robot. It's very similar for things like quadruped robots, who like quadruped robots are actually kind of well known in terms of their dynamics. They're also actually very stable systems. So they don't really require a lot of really fine control. When you get into like bipedal robotics, then it actually starts to get more difficult. We're technically a very under actuated system, such that if we start to lose balance, it can be impossible to recover. So if there's really difficult dynamics and they're really important for being able to solve the task, yeah, the gap between the sim and the real world is going to grow. And there's going to be more of a distance between those two for it to be useful. And there really aren't even simulators for this one because you can't even figure out how to model this in a simulator at all, really. The breakfast one, maybe sometime soon, we'll see. This one I'm actually working on a little bit, at least with a lot of my colleagues in the chemistry department to figure out how to simulate like even the construction of molecular processes. Because it would be pretty useful to have that information. We can investigate drugs faster, things like that. But this at the moment is hard to do even for like 3 molecules at a time, and it's really hard to simulate. So this is where, and the reason why I was having this discussion about like think about which tasks. If it's maybe more like training a robot to be kind of like mostly stable while walking, you can probably use a simulator for most of that problem. But once the agent starts to interact with the world in different ways, including contacts and other agents, simulators are going to have lots of gaps. Okay, any other questions? All right. Okay. So if you wanted to take that last route though, and look at maybe being able to train some models directly from video data, there is a good handful of data sets these days. These are basically all the ones that can be used for behavior cloning because most of these have the datas. They basically have X to Y, or what we tend to think of as state to action data. So these are all data sets that have big piles of what are essentially images labeled with the action that the robot took at that particular image. So then these could be used to actually do behavior cloning, some sort of policy training from these. And they're not typical, so they're not first person view data. Many of these are going to be like wrist camera data or like third person view of the workspace as well. But on the nice side, these all really don't have any dynamics mismatch problems. These are data recorded on the actual hardware from these robots. So if you went back and you played this data on the robot, you should get back the exact same motion that the robot replicated for these. So then we're just trying to figure out basically this mapping that goes from state to replicate this motion in the database somewhere that is supposed to happen at this state, and then train a big giant model to be able to do this because there's at least a growing pool of data. And this is essentially homework too, although you'll mostly be sticking to this data set because that one we can fit on our computer without too much trouble. Okay, so that being said, all right. So probably no any questions for these data sets? All right, because you'll kind of be showered with this data set for the next 2 weeks. So I think you'll get pretty used to it. And I'm going to go through a demo of this data set and not in a minute. All right, so we've got one last thing. We kind of covered this for a bit, but it's thinking about this data kind of like, is it easy or ease versus accuracy trade-off? And by accuracy, I really want to think about this. No dynamics mismatch versus easy to collect data, which usually has a higher dynamics mismatch. And that there's really this process of figuring out there's always going to be a trade-off between these two things for whatever type of data that's going to be collected for a particular problem. And that really, how is this going to work? Things that are going to be easy in this direction means that they're going to have more mismatch. And that basically there's going to always be this trade-off. In order to be able to train some robotic system that'll end up working out pretty well, there's definitely going to have to be some hard information, but there's usually more signal that's going to come from data that ends up being collected on like this end of the spectrum. Like it's purely exactly what the expert would do. So when thinking about the process of all right, what sort of system is going to be used to collect the data for this particular task? Because we had a chat now about kind of like difficulties between different tasks. Then also the next step is now thinking, all right, that's the task that is like desired to be solved. What is going to be the easiest way to collect data that'll provide enough signal for the robot to actually be able to solve that task? Because this is even related to, even at the trajectory level, got to make sure that inside of the images captured for that trajectory, there is the information that was used by the person to determine what is the thing that's most important for solving that particular task. Okay, does that make sense? Any questions? Okay, we'll probably revisit this a bit again for a few minutes on Friday before we start to get into on policy RL, where the whole idea after this is, okay, I'm tired of all this by hand data collection. We'll start to talk about how to automate our data collection, also known as reinforcement learning. All right, that's it for today. All right, take care, everybody.